Welcome back. This week we look at work and power, not just with things that move in a straight line like last week, but now with things that rotate. Now when it comes to rotation, we often use a term or a unit of a radian when we talk about the amount something rotates. So let's start off by looking at what a radian is. If you have a circle, such as a cake, let's pretend it's a birthday cake, and you take a piece of string and you snip it to exactly the length of one radius. So from the middle of the cake, you lay out a piece of string that reaches just to the edge of the cake. That piece of string would be one radius of the cake long. Now take that string and wrap it around the outside of the cake and mark off where the string started and where the string ended. Now cut out a slice of cake of that size. That slice would be exactly 1 radian of cake. Now if you were to slice up the rest of the cake into radian slices, you would achieve 6 full slices and a little bit of a slice, another 0.28 of a slice. And that's because 2 pi radians make up a full circle. And 2 pi, as we know, is 3.14159 times 2, which is, call it 6.28 odd radians in one full circle. Now up till now you might have been more familiar with measuring angles in degrees, and now we're introducing this new unit, radians. How do we convert between the two? Well, degrees is going to be the bigger of the two numbers, so we multiply by this ratio of pi over 180 to convert from degrees to radians. We want to make the number smaller, so numerator is small, denominator is big. And where this comes from is because 360 degrees is in fact 2 pi radians, so that means pi and 180 go together as the conversion. So just remember, degrees multiplied by pi over 180 gives you radians, and radians multiplied by 180 over pi gives you degrees. To understand the next concept, let's use one of these devices. This is a merry-go-round, which you would find in a children's playground. There's a central shaft and a bearing, and the children ride on it and they're able to rotate it, and it goes round and round. So here it is viewed from above, and for this example let's just assume that there's some issue with the bearing and it actually takes a little bit of torque to make it rotate because there's some friction. Okay, and to rotate it, let's pretend that a person walks around the periphery of the merry-go-round, obviously walking on the soil, on the ground, and applies a force that is perfectly tangential to the merry-go-round at all times. So here's the force initially. By the time that person has walked to this point, the force would be horizontal, and then this way, and then vertical, etc., etc., till the person had done one full rotation. Now, would that person be tired after doing that work, after rotating the merry-go-round by one turn? Well, it stands to reason. If you've done work, if you've applied a force through a distance, then you would be tired because you've done some work. So in straight line terms, we knew that work done was force times distance. So effectively, how far had this person walked? From here all the way around back to here is effectively one circumference of the circle. Now circumference is 2 pi r. So the force was applied through a straight line distance of 2 pi r. And force, after all, is torque over radius. Where does that come from? Well, torque is force times radius. So force multiplied by radius is torque. So we can replace force with torque over radius. The two radii terms can cancel out, and we are left with torque times 2 pi. But now, if we remember what we did moments ago, we learned that 2 pi radians was indeed 1 revolution, which is the distance that this machine turned through. So how about we replace the theta in the term goes in place of the 2 pi, because whatever portion of a turn you rotated through would be taken care of if you just simply put this term in as theta radians turn through. Let's start by looking at this very simple number 8. It says a torque of 105 Newton meters is required to rotate a pulley. Determine the work done in giving the pulley 1 revolution. Okay, and then if the pulley makes 80 revolutions per minute, how much work is done per second. Remember that work done per second will in fact be power. Okay, so work done by a torque is the torque multiplied by the angle rotated through in radians. And they said it was 105 Newton meters, that's the torque, and one revolution is in fact 2 pi radians. So 659.7 joules is the amount of work done. Then let's consider 1 minute. So in 1 minute, the work done would be 659.7 times 80, because remember it did 80 full revolutions in a minute. And we put in time below because we are trying to find power. Power is in fact work done over time. So there's the work done. The time in 1 minute is 60 seconds. So 879.6 watts is the rate of doing work, or put another way, the power. Now, a number of the problems that follow relate to mines and winches in mines, hoists in mines. So I'd suggest you go and look at this little YouTube clip. Either you can type it in here or you can go to the notes and click on the link. And once you've done that, you'll better understand this little sketch, which basically describes what happens in a mine. What you have is a winch winding up cable. The cable goes around a big pulley, which they call the sheave wheel, and down the mine shaft, which is essentially a hole in the ground, you have the mine cage, and in it are people and goods, and the winch operator controls the descent and ascent of the mine cage and the skip. And they sometimes stop at different heights. These are called stopes, where the miners are mining the ore horizontally into the ground. So once you understand that concept, you'll be better equipped for the problems that follow. Let's start with number 29. It says a machine of mass 1800 kilograms is raised by a chain wound around a drum that can rotate. The load is initially 20 meters below the axis of the drum, and the platform to which it is being lifted is 3 meters below the axis of the drum. The chain weighs 36 newtons per meter, so that's got to be taken into account when we work out the work done. Determine with the aid of a suitable work diagram the total work done during the lifting operation. So here's the setup. Here is the winch drum. Here is the cable that is going to be wound up onto the winch drum when it rotates anti-clockwise. These double arrowheads indicate that there's tension in that green cable, and we're going to be interested in what the tension is up here at the top. And then here are the heights. This is where the 1800 kilogram load that you are lifting started out, 20 meters below the axis of rotation of the winch drum. And it goes up to this level, which is 3 meters below. So essentially it's going to travel 17 meters vertically. And finally, the weight of the cable is 36 newtons per meter. Every meter, if you were to cut off 1 meter and lay it on a scale, it would have a weight of 36 newtons. Let's consider the tension in the cable up here where it meets the winch drum. Now initially, at the start, we have the full 1800 kilograms of mass as a weight. Obviously, once you multiply by 9.81, that is the weight to lift it. So this cable would be supporting that, plus the cable itself. So the tension up here would be the sum of those two, the 1800 times 9.81 to take care of this piece here, and then the 20 meters of cable, so 20 times 36, because it is 36 newtons per meter, would give you a total of 18,378 newtons of tension in the green cable there where it meets the winch drum at the start of the operation. At the finish of the operation, much of that cable is wound up and is now sitting on the drum. All that remains is the 3 meters, because remember that this weight went from where it is in the drawing up to here, and there was still 3 meters of cable remaining. So take that into account. There is 3 meters of cable remaining, which is being supported, times 36 newtons per meter, plus you're still supporting the full 1800 kilograms of mass. So this tension, by the time you finish the operation, will be less than it was at the start. It will be 17,766 newtons. Now for the work diagram that is asked for. Basically, that's a graph. Let's use force and distance. And remember that the product of force and distance is work done. So that means for us that areas in this graph will represent work done. That's why it's called a work diagram. Okay, so let's plot the starting force that we were dealing with, which was 18,378. And remember, as you lift the mass, so that diminishes until right at the end it is 17,766 newtons. Now that would reduce linearly, meaning that this is a straight line. Okay, so we are interested in the work done for this whole operation, which would essentially be the sum of these two areas, because remember, area is basically whatever you get when you multiply these two terms, and we know that that's work done. So the area of this triangle plus the area of this rectangle would give us the total work done for the entire operation. So to lift this 1800 kilogram mass and the cable from start to finish is going to take 37,224 joules of work to achieve that. And that was obtained by taking the triangle, half base times height, plus the area of the rectangle, base times height. So there's your total. Remember, the height of the triangle is this number minus this number, which gives you this piece here, multiplied by this, multiplied by half, gives you the area of the triangle. Here's another one, number 37, which is virtually identical to the previous one. So I would suggest that you stop the video shortly and attempt this one. And once you have made a decent attempt, only then continue the video and look at the solution. Basically what happens is you have a loaded mine cage with a mass of 8 tons, and it's hoisted in 3 minutes 15 seconds from 220 meters depth right up to the surface at a steady speed by means of a single wire rope of mass 2.911 kilograms per meter. You must find the average power required. Now, average is important here because the power requirements will change. They will become less as the rope is wound up onto the drum. Second, the work done in hoisting the loaded cage together with the rope from 220 to 80, from 220 meters depth to a depth of 80 meters. Remember, depth is referring to distance from the surface down to a point, from the surface down to a point. So once again, we'll look at tension at start, tension at finish. At the start, we had 8,000 kilograms as well as 220 meters of rope. Now the rope had a mass of 2.911 kilograms per meter. We must multiply that by 9.81 to get newtons per meter. So we started out with 84,762 newtons of tension, and that tension is up here where the cable meets the drum. At the end, we still were lifting the 8 tons and no rope, so because we went right to the surface. So 78,480 newtons. Here's our work diagram, much the same as before. The tension diminishes from 84,763 linearly down to 78,480 newtons, and the distance traveled through was 220 meters. So the work done is once again a triangle, half base times height, half base times height, height being the difference between that number and that number, which would give you this little piece here, plus the area of the rectangle, which is 78,480, which is the height of the rectangle multiplied by the distance across. So 17.96 megajoules is the amount of work done for this operation. And they said it happened in 195 seconds. So the average power would be work done over time, which would give you an average of 92,102 watts or joules per second. Now remember, this is average. If you were to specify a motor of 92 kilowatts for this operation, it would not work, because in the beginning it would require more than that, and at the end it would require less than this. So you must use maximum power if you are specifying, for example, the size of the motor to drive the machine. But in this case you were asked for average, and this is the average power. Now there's a second part to that number 37. They want to know the work done in hoisting the loaded cage together with the rope from 220 depth to 80 meters depth. So it's similar to the previous one, except we're stopping 80 meters short of the top. So once again, tension start, no problem with that. Tension finish, you would still have the 8 tons that you're lifting, the 8,000 kilograms, but there would be 80 meters of rope remaining. This piece remains. And 2.911 kilograms per meter times 9.81 added to that, and you have 8764 newtons at the end. So it all looks very much the same. You start at 84,762, you end at 8764, but you only travel 140 meters. Note 220 minus the 80, you only traveled 140 meters. So the work done is the area of the triangle, half base of 140 now, times height, which is the difference between that value and that value, plus the area of the rectangle, which is 8764, multiplied by the 140. So you are at 11.587 megajoules. Now to test what you've just learnt, here is a little example which I'll explain, and then I want you to turn the video off and attempt it. It says a winch lifting a load of 1200 kilograms at constant velocity is depicted. The load is initially 93 meters below the drum and is raised to a position 10 meters below the drum. The work done in raising the load is, and you've got a multiple choice scenario here, and then they say if the lift takes place in 2 minutes, the average power required is one of those. You've just done one like that. And then the shaft torque at the start of the lift is, remember the torque is force times radius, you'll have to figure it out. And finally, question 4, the angular velocity of the drum during lifting is angular velocity. Remember, omega measured in radians per second or revs per minute. In this case, they want revs per minute. You'll have to make the conversion. So stop the video now and make a reasonable attempt at that, please. D, C, A, and E. You can have a look at this solution. Right, now we move on to the section on force, mass and acceleration. In your textbooks, it's page 169, number 4, chapter 14 rather. In these notes, it's 15. And up till now, virtually all our problems were ones where there was constant velocity. So everything was in equilibrium. Forces left were equal to forces right, forces up were equal to forces down, forces up the slope were equal to the forces down the slope, etc. But now we know from Newton's laws that when we have acceleration, we don't have equilibrium. So forces no longer balance. But here's the plan that we tend to use throughout engineering. We introduce what is essentially a fictitious inertia force to bring the problem into so-called equilibrium, to allow us to continue to sum as we are used to doing. Now the textbook approaches this slightly differently, and various people do the same, but what we are going to do for the sake of this course is we are going to apply our forces as before. Here is, for example, a little motor car that is accelerating from left to right. Well, let's start with the fact that it's moving from left to right. So there's our motion double arrowhead. And it's also speeding up. So our acceleration double arrowhead is in the same direction as motion, which would suggest that this motor car is traveling faster and faster and faster from left to right. And to achieve that, as per page 172, where Newton's laws are depicted, we understand that there must be imbalance. So the tractive force has got to be bigger than the tractive resistance. And if that's the case, you will achieve acceleration from left to right. That's fine. But now we would like very much to make our problems balance so that we don't have to learn new rules and we can simply equate lefts equal rights. So to do that, we insert a force that is the product of mass and acceleration. And we simply always put it in the opposite direction to the acceleration. So you inspect the problem and decide that acceleration is to the right, and then in the opposite direction, through the center of gravity, if you know where it is, you insert this little force, which I'm going to make red, so we remember that it is in fact fictitious, and it is mass times acceleration. Once you've put that in, now you can sum lefts equal rights. And in this case, you would have TF is equal to MA plus TR, and you could continue as though it was a statics equilibrium problem. Let's start with this jet plane on page 173, number 1, where we have a thrust of 26.75 kilonewtons, pushing the jet plane from left to right, and only 8.92 kilonewtons resisting. So it stands to reason there's imbalance, and that acceleration is going to occur in the direction of motion. In other words, this aircraft is going to be going more and more quickly as time goes on. In other words, it's accelerating. Okay, they tell us the weight of the aeroplane, and they tell us that the air resistance is 8.92 kilonewtons. That's already in the equation there. Okay, we've got to find the acceleration and the time taken to accelerate from one speed to another speed. Let's start with summing the forces horizontally, lefts equal rights. Now remember, we can only do that once we have inserted the fictitious inertia force. So if we know acceleration is to the right, let's insert MA through the center of gravity, if we know it, in the opposite direction to acceleration, which in our case is going to be to the left. So we need to know the mass of the aircraft, and there we multiply it by acceleration. Okay, so what do we have? Forces to the right equal forces to the left. We've got 26.75 kilonewtons to the right, and to the left we've got 8.92 kilonewtons, as well as 7277.5 A. Now that is the mass. How did we find the mass? Well, we know that the weight is mass times G, so mass is weight over G. We were given the weight, divided by 9.81 gives us the mass in kilograms. That's where that came from. So we can deduce that acceleration must be occurring at a rate of 2.45 meters per second, or meters per second squared. So let's go back to the mines for the next problem. The only difference is we're now going to bring acceleration into the equation. So we have a mine cage, mass of 1 ton. Determine the tension in the cable when the cage is ascending with an acceleration of 0.6 meters per second, or meters per second squared. And then when the cage descends a distance of 20 meters in 25 seconds from rest with uniform acceleration. So we'll do that afterwards. So here we have the winch drum rotating clockwise, winding up the blue cable. We have tension where the cable meets the drum. We have a mass of 1,000 kilograms, which is ascending, but doing it with increasing velocity. In other words, accelerating upwards. So as before, we're going to have the tension, which is a force upwards on our mass that we are lifting. We have weight, which is always present regardless of what's going on. That is the gravitational pull of the Earth, mass times G. And this one is bigger than this one, and that's why acceleration is occurring upwards. And that is where our imbalance is. Now remember what we're going to do to make it sum easily and handle it exactly the same way that we've been handling our statics equilibrium problems. We're going to insert the fictitious inertia force. Remember the rule, opposite to acceleration. So in other words, in our case, downwards. And it is always the product of mass times A, not weight, mass times acceleration. So we're going to insert it over there. And provided it is in, we can now say that equals that plus that, which is what I've done here. So we have mass times 0.6, because we were told acceleration was happening at a rate of 0.6 meters per second squared, plus mass times G, which is 9810. So the tension is 10410 newtons. Now in the second one, we actually have the mass descending. Okay, and it is also doing it with acceleration in that direction downwards. And what we are told is that it descends a distance of 20 meters in 25 seconds. But they don't tell us the acceleration. So if we look at our equations of motion, let's find an equation of motion that involves all the knowns and the unknown that we desire. So S must be in there because we've got distance. Time must be in there because we are told 25 seconds and we desire A. So S equals ut plus half at squared makes sense. Next is to pick a sign convention. I will just make up positive, which whatever you prefer. You could make down positive if you prefer, but I'm going to make it up. So S traveled is minus 20 because it was from here down to here, downwards opposite to the sign convention. So minus 20 is the distance traveled, equals ut, it started at 0 velocity, so that term is always 0, plus half times the unknown acceleration times the time of 25 seconds, that's what gets squared. So the acceleration is 0.064 meters per second squared in a direction that is downwards because of the negative sign. Right, now forces. Weight is 9810 newtons, the gravitational pull of the Earth. In the cable, even though it is descending, there is tension. Now be very careful here with your arrowheads. Because of the motion being downwards, you might be tempted to make this arrowhead downwards as well. That's not correct. The point is, even with a cable that is descending, and that cable is tight, as is the case here, you always have your arrowheads facing each other. Remember, right at the beginning we learned that tension is always denoted by two arrowheads facing each other. The arrowhead relevant to our weight is the one closer to it, so that is an upward arrowhead, even though we are descending. So this weight feels upward T, downward 9810, and this one is in fact bigger than this one, and that is why we are achieving the downward acceleration. So that's the imbalance. But remember, we are going to bring it into so-called equilibrium by inserting the fictitious inertia force. The rule is simple: opposite to acceleration. Decide which way acceleration is, place this red arrow opposite to that arrow, and it is always mass times acceleration. So what we're left with is 2 ups and 1 down. T plus 1000A are up and 9810 is down. We can solve for the tension in the rope at 9746 newtons. Now to practice all of that, I'd like you to do number 5. Stop the video, and only once you have worked out all 3 of those, only then restart the video and check your answer, please. Next, let's look at this number 9. A 1.5 ton car traveling at 63 kilometers an hour has its speed reduced uniformly to 18 kilometers an hour. So it went from 63 to 18 kilometers an hour over a distance of 22 meters. Determine the retardation in meters per second, in other words, the acceleration in meters per second squared, and then the retarding force. So that is the force that is causing this retardation to happen, and then see how long it took. Initial velocity u, 63 divided by 3.6 to convert from kilometers an hour to meters per second, suggesting it started at 17.5 meters per second and it ended at 18 kilometers an hour, which is 5 meters per second. Distance traveled 22 meters. Pick an equation of motion that has all the knowns that you have in it as well as the unknown. Now we want A, and we have u and v. So the only one that has all of that is v squared equals u squared plus 2as. So we have v at 5, u at 17.5, 2 times a times the distance 22 meters. So to the right is obviously positive, and it comes out with a negative acceleration of 6.39 meters per second squared, which is the answer to A, which is the deceleration or retardation. Next, we've got to find the force that caused this, the braking force, in other words. So if you were traveling along in your motor car and you applied the brakes, the motor car would feel a braking force at the surface of the road in the opposite direction to your motion. Okay, so we'll make that the green force. And that is in fact the only external unbalanced force causing the acceleration. But remember, we like to bring it into so-called equilibrium by inserting the fictitious inertia force, which I'm making a red to remind us each time that it is in fact fictitious. The rule is simple: opposite to acceleration. Acceleration is left. We're going to make this then right, and it is always the product of mass and acceleration. We know the mass and we now know the acceleration. So braking force is simply 1500 times 6.39, 9.585 kilonewtons. Finally, how long did it take? So we need an equation of motion with a t in it. and also as many knowns as possible. So v equals u plus at will work for us. Final velocity is 5, initial is 17.5, plus the acceleration, which is negative 6.39, times what we desire, which is the time. From that you can determine how long it took. Next, let's consider a rocket, such as the one depicted over here. So let's look at number 10. It says a rocket of mass 727 kilograms is fired vertically upward. If the resistance to motion through the atmosphere is 3.5 kilonewtons and a constant thrust of 53.5 kilonewtons is maintained for the first 12 seconds. Find the acceleration during the 12-second period, and then secondly the velocity at the end of the 12-second period, and then C, the maximum height reached. So let's start with that first 12-second period. We have 53.5 kilonewtons of thrust. We have the rocket's weight, which is its mass times g. We have the resistance to motion, which is the aerodynamic drag. And we would have big imbalance between this and the sum of those two. This would be bigger than the sum of those two, meaning that we achieve acceleration upwards. Okay, but now to bring it into so-called equilibrium, we insert the fictitious inertia force. Remember, the rule is simple. Opposite to the acceleration, in other words downwards, the product of mass and acceleration. Now we can sum as though it was a statics problem, and we have up equal to 1, 2, 3 downs, 1, 2, 3 downs. So we find that the acceleration is 58.97 meters per second squared, which happens to be 6g if you divide by 9.81. If there were occupants in this rocket, they would be experiencing 6 times the normal gravitational pull that we experience as we sit here normally. So how fast would we be going after the 12 seconds? So we need an equation of motion that's got final velocity in it, and as well as the other knowns that we have and the unknown that we desire, which is, that was v. So we need to know how fast we are going after 12 seconds. So v equals u plus at. U was 0, acceleration was 58.97, and we are dealing with 12 seconds of time. So 707.64 meters per second is how fast it's going after 12 seconds. How far would it have traveled? Equation of motion, S equals ut plus half at squared will work. And we have u at 0, half times a times the time, 12 seconds squared. It would have traveled 4245 meters, 4 and a bit kilometers. So to sum up, at the end of the 12-second period, we are traveling at 707 meters per second, and we are 4245 meters above the surface of the Earth. But now C asks for the maximum height reached. Now remember, this rocket doesn't miraculously just stop there. It now possesses this massive velocity. It is at this height, and it's going to continue going. The engine is now off until it reaches a maximum. So now we look at the scenario from the end of the 12-second period until the rocket comes to rest momentarily at its highest point. During this time, it is indeed moving upwards, so motion is upwards, but as I'm sure you'll all agree, it would be decelerating. The engine is off, and it is now coasting up to the highest point. Once it reaches the highest point, yes, it will turn around and come down again. We're not interested in that. We're interested in what happens between engine off and 0 velocity. Okay, so it's moving upwards but decelerating. Whilst this is happening, we still have the aerodynamic drag, we still have the weight. But now we have to introduce MA in the opposite direction to acceleration, which is amazingly straight up. And it is M times A. And we would like to know what that A is. Okay, so we have 1 up, 2 downs. 727A is up, 3,500 plus the weight is down. So it suggests that we are accelerating at 14.62 meters per second squared. So finally we need to work out how far the rocket traveled from when the engine was switched off until it came to rest. So final velocity will be 0. So we can use v squared equals u squared plus 2as. And let's make the sign convention down as positive. Remember, this was in fact a deceleration, but by inspection we'd already decided on its direction. So to finish off, we'll just make the sign convention such that down is positive. So the acceleration was down at 14.62, so it's positive, no problem there. But the initial velocity was upwards, which is negative 707.64 meters per second squared. But it is going to be squared, and that negative is going to become a positive. And you find that the distance traveled from engine switch off until it comes to rest is 17,124 meters. Now we must add that to the 4245 traveled previously, and we'll determine that the rocket came to rest at 21.37 kilometers above the surface of the Earth. Okay, let's look at number 11 next. We have a man standing on a scale in a lift. So a man of mass 72.7 kilograms stands on a scale in an ascending lift that's going upwards. If the lift starts from rest and the scale reads 800 newtons, determine the speed of the lift after 5 seconds. Also, what is the force during the 5-second period in the steel rope supporting the lift if the total mass of the lift, the scale and the man is 1090 kilograms? So that'll be the B part. So this is a good example to practice free body diagrams. So here is the whole machine, the cable, the lift cage, the scale and the man standing on it. And then if we zoom in and we look at just the man, we can draw a free body diagram of just the man. So here's the man. Here is the non-negotiable force, which is weight, always present regardless of what's going on, 72.7 times 9.81. That acts downwards towards the center of the Earth. Here under his feet is compression. Now remember that compression is 2 arrowheads away from each other. The man feels the up arrowhead, the scale feels the down arrowhead. Newton said for every force there's an equal and opposite force. And because the scale is reading 800 newtons, it suggests that it is being pressed downwards on its top surface by 800 newtons. And it follows that the equal and opposite force is pressing the man under the soles of his shoes upwards with 800 newtons. So when we are drawing just the man, we must insert that as an arrowhead upwards of 800 newtons. And remember that this one is bigger than this one, and that is resulting in the upward acceleration. Another one of Newton's laws said that if there's imbalance, acceleration will occur in the direction of the imbalance. But we'd like to sum things, so we insert the fictitious force. The rule is easy, opposite to acceleration, always the product of mass and acceleration. Once it's in, we can treat it like a normal statics equilibrium problem, and we can say 2 downs equal 1 up. And from it we can find that the acceleration must be 1.194 meters per second squared upwards, because we have 1 up and 2 downs, sum to find that. So how fast is the lift going after 5 seconds? Well, V equals U plus AT will be nice to work with here. Starting at rest, so U is 0. 1.194 is the rate of acceleration. It happened for 5 seconds. So we have 5.97 meters per second as our final velocity after 5 seconds. Now we zoom out a bit, and our free body diagram involves more than just the man. It is the cage in its entirety with its contents and the cable supporting it, and we've got to find the tension in that cable. So as a whole, the whole cage with its contents is 1090 kilograms of mass. Multiplied by 9.81, there's our gravitational pull acting on the entire lift cage. The lift cage is supported by a cable in which there's tension. Tension always has 2 arrowheads facing each other. And looking at the big picture, motion is still upwards. Acceleration, we now know, is upwards, and we even have a value for it. So the tension in the cable is equal to the sum of these two. Remember that this one is the fictitious inertia force applied opposite to acceleration, in other words, downwards. What is it? Product of mass and acceleration. So we have 2 downs equal to 1 up. 2 downs equal to 1 up. So that force up, which is 11,994 newtons, is the tension in the cable. Now we're going to finish off this section with number 12, which gives learners quite a problem because of this little bit of complexity of the mechanism. What we have is a frictionless pulley. So this pulley over here rotates without friction. It's also inertialess, by the way, but we don't want to bring that into play just yet. Over which passes a light cord. Light cord simply means we don't have to consider the weight or the mass of the cord, which has weights hung from its end. So there's a weight on either side of this cord. Now the arrangement is released from rest in the position shown. So here it is, it's held, and then somebody releases it and starts a stopwatch. The arrangement is released from rest in the position shown, right? On arrival at the ring, the 18 Newton weight passes through the hole, but the 27 Newton rider is arrested. Now that's what gives everybody the problem. Here is a bracket, and it's shown in cross section, hence the hatching lines, but here is a hole. Now that hole is just big enough to allow the 18 Newton weight to pass through without touching it, but clearly the 27 Newton weight, which is annular in shape, and which by the way is just resting on top of the 18 Newton weight, it cannot pass through the bracket, obviously. So if this contraption goes downwards, the 18 Newton weight goes through and continues, and the rider, this donut-shaped object, stays behind, resting on this bracket. If you understand that, then it is an easy problem to do. They say determine the height from the starting position, that's here, through which the 18 Newton weight descends. So how far from where it is, it starts 50 above the bracket, and it will pass through, and then it will stop, and it will turn around and come back again. Now we're not interested in the coming back again. We want to know, determine the height from the starting position through which the 18 Newton weight descends. Now to start off with, it's obvious that the left hand side has more weight than the right hand side. So 27 plus 18 is definitely more than 27. So the moment I release this lot, it is going to move down and up anti-clockwise. Let's do that again. These two weights are going to go downwards, this weight is going to go upwards, and this pulley is going to rotate anti-clockwise. So to start with, we're going to have motion down, motion up, acceleration down, speeding up, acceleration up, speeding up. Then the 27 Newton weight gets taken out of the picture, and suddenly from that point onwards 18 is less than 27. So we're going to have deceleration, and ultimately it's going to come to rest at a point. So there are three significant events here. There's the start, where we are now. There's the second significant point when the rider hits the bracket. And the third significant point is when the system stops. That's where we finish with the problem. After that we know it will return, but that's not a matter for us to worry about. We're interested in start as drawn, B when the rider hits the bracket, and C system coming to rest. So now I'd like you to stop the video and make a reasonable attempt at this one before looking at the solution. So those three significant events. Event 1 is the start, event 2 is rider hits bracket, event 3 is system comes to rest. First things first, we're going to go 1 to 2, here to here, and we're going to draw what we have during that instance. So we have our pulley, we have tension on this side, tension on that side. Arrowheads towards each other, arrowheads towards each other, regardless of motion and acceleration. If there's tension, that's what they look like. Then we draw in our motion, which is downwards on the left, upwards on the right. It is speeding up, so acceleration is in the same direction as motion, which is downwards left, upwards right. Then we put in weight, which is 45 for the total of the 2 on the left, and 27 for the 1 on the right. Both of those act towards the center of the earth, not negotiable. Okay, then to bring us into so-called balance, opposite to acceleration, we put in MA, which would be M, which is weight over 9.81 incidentally. That's how you get to M. Weight divided by G gives you M, and M times A goes in opposite to acceleration, in other words upwards for the left hand side and downwards for the right hand side. So on the left you have 2 ups equal to 1 down, 2 ups equal to 1 down, and you have an equation. On the right you have 2 downs equal to 1 up, 2 downs equal to 1 up. But the crux of the matter is the tension around a frictionless, inertialess pulley is identical on both sides. So T1 is in fact equal to T2. So you can put those two as equal to each other. That equals that, because of the fact that T1 equals T2, and you can find that acceleration is going to occur at the rate of 2.45 meters per second squared. Okay, how far are you going to travel? Well, you're going to travel 50 millimeters from 1 to 2, and then some distance beyond. So let's start by finding how fast it is going when it reaches position 2. So if it is to travel 50 millimeters, and we want to find how fast it's going at that point, let's use v squared equals u squared plus 2as, and we find that 0.495 is the velocity at position 2. Position 2 being when the rider hits the bracket. Now we've got to consider position 2 to position 3, where things change significantly. Motion is still downwards on the left, upwards on the right, but it is now going to slow down from here onwards. And the reason for that, we discussed at the beginning, the left-hand side now suddenly has less mass than the right-hand side. So it is going to slow. So acceleration is in the opposite direction to motion. Acceleration is in the opposite direction to motion. Tension and tension are still present. Remember, those arrowheads have got nothing to do with motion. They just indicate tension. So we have also got to put in our weights. Those don't change other than the number changed. It's now 18 newtons downwards on the left and a greater 27 on the right hand side. To make it so-called balance, bring it into equilibrium, fictitious inertia force opposite to acceleration, in other words down left, up right, and we must have mass times acceleration. Mass is weight over g, weight over g. Okay, so on the left we have 2 downs, 1 up, 2 downs, 1 up. On the right we have 2 ups, 1 down, 2 ups and 1 down. And as before, over a frictionless, inertialess pulley, the tension on both sides would be identical. So once again we can equate this to this, and we find that the acceleration is 1.97 meters per second squared. You won't necessarily get a negative sign because you have already by inspection decided on the direction of acceleration, so you're just getting a value. We know it to be deceleration. And now for the final step, to see how far it's going to travel from 2 to 3, decelerating at that rate. So final velocity is 0, we know it comes to rest. Initial velocity 0.495, we're making downwards positive. And we have 2 times the acceleration, which we know is 1.97. We've set our sign convention for this little part as downwards positive. And we find it travels 0.062 meters from position 2 to position 3. We must add that to the 50 millimeters that it took to go from 1 to 2, and the total distance traveled